So let me go for addition. Addition is very important for us in a digital circuit design. Why? Because the entire operations that we are doing, especially subtraction operation, we are doing with the help of addition only by using uh, subtraction. Also, we are converting to addition with the help of ones and twos complement that we will discuss later when we go for subtraction operation. Now these are the steps to be followed. First, write down side heading half adder. In the addition, we are in a adders. Write down side heading adders. In that we are going. I'm explaining now a half adder. Why this is a half adder? I will explain. So this is what in electronics an adder or a summer is a digital circuit that performs addition of numbers. So see here half adder. Half adder is what? First of all, let me explain. So see here, just a minute. Okay, so let me take a example. No, let me take a and a plus b. Okay, so till now we discussed regarding a as 8 bit or 16 bit. Try to concentrate carefully. We know we considered a as one register, b as one register, and we considered as 8 bit and b as 8 bit. And if we want to consider as a nibble, it will be what? It will be 4 bits. Nibbles, a nibble size, everyone knows that nibble is 4 bit, right? So if it is a nibble, it will be 4 bit. But before going to the actual concept, everyone must know about how what happens if we add one bit and one bit. We need to design a circuit for only one bit and one bit so that we'll get the corresponding output. So for that everyone knows that I'm not going for 8 bit or I'm not going for a 4 bit. I'm initially taking only one bit. Means a equals to one bit and b equals to one bit. Okay, is it clear now? So I'm not going initially for designing a circuit of 8 bits and 4 bits. It will become more complicated if you're not understanding a one bit concept. So initially I'm going for one bit and one bit. So if you add 1 and 1, first of all, this is your problem. What is a problem statement is addition of two numbers, and the two numbers is only one bit. The capacity of that is only one bit. So we are adding one bit. So if you add one bit, what your output generated will be what one? If I want to add one, just answer me, as everyone knows binary addition, right? If you
Zero
if
one.
you 0 1, so means what? Output should be considered two variables or one variable. One I should consider for sum, for storing the sum as 0, and one I should consider for storing the carry as 1. Okay, so how many inputs will be there? How many outputs will be there according to this problem statement? So I want to add two one bit numbers, and the output generated will be 0 1, and 0 must be placed, so output will be of two variables. One is for storing the sum and one is for storing the carry. Is it clear problem statement? So in this is your circuit, this is your combinational circuit, and the two inputs that you're giving, that is nothing but a and b. The storage capacity of a is only one bit, b is only one bit. So the output generated, if I give 0 1, let us consider 0 0, means what? The sum will be 0, so you need to consider the output as, so as according to the problem statement, everyone knows that there are two inputs and two outputs. And after that we need to give the next step is we need to assign the letters for that. So we assigned a b and s c, sum and carry. Okay, so if it is 0 0, the result will be 0, and the carry will be 0. Now let us suppose, as there are two combinations, let me draw the truth table. Next concept is, after assigning the input variables and output variables, after assigning the letters, the next step is to, which is to write the truth table. One side is your input combination and the other side is your output combination. Next is what? So input is what? A, B, and output is what? Sum and a carry. And output is sum and carry. Is it clear, everyone, until this concept? So now, if it is two inputs, how many combinations will get? 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. Okay. So now, according to, everyone knows the rules for addition, 1 plus 1, 1 plus 0, like that. According to this, what will be the sum of fast? If you know binary addition, then you can able to answer this. What is the result of sum? 0 plus 0 is 1. The result is 0. And the carry generated will be what?
0.
0. Okay, next is what? 0 plus 1. The sum will be what? Carry will be what? Sum will be,
1 carry 0.
okay, 1 plus 0. 1 plus
1
0. 1, 0.
0.
1 plus 1. The
Sum
sum will
0
be,
carry 1.
okay, sum equals to 0, carry equals to 1. Until here it is clear, right? Next step is what? Next step is what? Next step is simplified boolean expression with k-map. Simplified boolean expression with k-map. So how many outputs are there? One is for S, one is for C. So you need to write for S one k-map, and for S you need to write one k-map. You need to write one k-map. Okay. So this is your k, this one. So I want your expression. If you can answer A, B. This is for carry. This is for sum. A, B. Okay, so this side will be A complement A. Next is B complement B. Okay, so where I have to place one in the carry, and only is the 1 1. So when there is 1 1, so when there is 1 1, we have in the carry output as 1. So in this place I have to place 1. Okay, now what about sum? So in sum, if there is 1 and 2, the output generated is 1. So where I have to place 1? In place of 1 and in place of 2, I have to place 1. In the remaining places it is 0. Okay, it is 0. Now grouping. Now grouping. So grouping is what? I have to group this one and I have to group, I cannot group as diagonally. So this is your grouping. Now tell me the expression for C. Tell me the expression for C. So what is the expression for C?
AB.
It is
AB.
AB. Okay. Now tell me the expression for sum.
A complement B. A plus
A,
AB complement.
okay, A complement. Let me write here A complement A, B complement B. Okay. So if you see here, we'll get A complement B plus A B complement. This can also be written as what? Yesterday's concept I explained. This can also be written as,
A XOR B.
yes, ma, very good. So A XOR B. Okay. So why I am writing this as A XOR B means you must know the XOR truth table. So for 0 0 0 1 1 0 1 1, the output for XOR will be what, ma? Is it odd one detector? Yes, XOR is odd one detector. Means what? You will get 0 1 1 0. Means what? Means this one you have to consider, which is A complement B plus this one you have to consider, which is A B complement. So finally the XOR, we are getting XOR, so which is nothing but A XOR B. So that's the reason that we are converting A complement B plus A B complement to A XOR B. Okay, is it clear? So next step is what? Fast. Note down in your notes, ma'am. The design statement, the designing for half. Why I'm saying half adder? Let me explain after completion of all this. So our main design is to add a two single bit digits, and finally the corresponding result will be sum and the carry. Okay. So for that we started with the problem statement. With this we identified that there should be two inputs and two outputs. Based on that we have designed our corresponding truth table, and after that we have converted that. We need to simplify this expression. For that we have written a two variable k-map, as we have two inputs for this and two variable k-map. After this two variable k-map we simplify the expression until this. Next, last step is what? Last step is what?
Logic diagram.
Logical diagram. So for this logical diagram, so you must know, as we have what? As we have a XOR B. First of all, you must know XOR gate, how it looks like. So one is A and the other one is B, and the next one is XOR. So this is your XOR, and the output for this will be S equals to A XOR A XOR B. Okay, A XOR B. And the next is for carry also you have to take. For carry, as we have A already here, B already here, and simply the operation that we use here is AND. So try to consider and this is the output for C equals to A B. Okay, in this way you have to draw, and the other way is what? Try to take this one. Try to take this one. So if you take this one, what we will get, no? So instead of using a XOR operation, I want to use the same expression that we have here: a complement b plus a b complement. So for that, what we will do, directly write as a in this way. Next, a complement, a complement. Next is b. Next, b complement, b complement. Next is what? A complement. This one is a complement b. There is an operation called AND. Next, a b complement, a b complement. There is an operation called and between there is a or. There is a or complete. Okay. Next, in the same way, a b. This is S and the other one is C. So this is a b. This is your C. Okay, so in this way you can represent either in two ways the logical diagram. Either this one is also correct, this one is also correct, but the simplified version is this. We substituted AX or B. Okay, is it clear, everyone? So see here, ma. So this is your half adder. You have to mention like this: half adder circuit. We have added A, B, and the generated is sum and carry. And this is your XOR operation. This is the one. So XOR and so A, B, and the carry generated is A XOR B. You should not write like this sum and carry. You have to express. You have to give the expressions in expression. So S equals to A XOR B, carry equals to AB. Okay, or see here, a complement b plus a b complement, and this is your truth table that we have done for carry. And for sum, k-map simplification for half adder. This is for carry, this is for sum. Next, I want to show two representations that we followed. The two representations are that we followed is, one is this one and the other one is this one, and the other one is what? This. Okay, so it is not represented as a x or y, it is represented as x y complement plus y complement x. Okay, either way is correct. So this is your half adder. Now can anyone tell me what is the drawback of half adder in this? Why, if you add two one bits, let me explain. Until here it is clear. So let me explain why this considered as half adder. Okay, why? Because whenever you are doing addition, let us consider a 0 1 1 1 0 1. Try to concentrate. So what we have selected, we have selected two 1 bits. Okay, so two inputs we have considered, one is A and the other one is B. Okay, so don't concentrate on the size of A. So previously we considered only 1 bit, but what happens if you want to add 1 and 1? The problem here arises is, see here, 0 plus 1 is 1. So 1 plus 1 is, the sum will be 0 and the carry will be 1. Next time, how many bits we got for this? How many bits we got for this one? So from this there is a carry generated and this carry need to be added. So this carry need to be added. For that, how many bits we are adding? 2 bits or 3 bits? 3 bits
3
we
bit.
are adding. So if there is a case of like this, so it does not affect, the previous concept of adding 2 bits is not sufficient. So that's the reason it is mentioned as half adder. For making this all 3 to be added, we need to go for full adder. So try to concentrate. So whenever you are adding, if there is a carry generated, that carry will be forwarded to the next bit. So whenever you are forwarding to the next bits this one, so when you combine, we have what, how many bits? Totally 3 bits. So if you want to add this 3 bits, first of all the input should be what? The input given for the design should be 3 bits. But how many inputs that we assigned for half adder? Only 2 inputs. If carry is generated, that carry we are not giving as input. So that's a problem in half adder. So that, because of that, we are going for a full adder. Now in a full adder, how many will be the input bits? How many will be the output bits? Answer and tell me. I have given a problem statement that there is a problem in a half adder, saying that if there is a carry generated, we could not add to that, as the input that we have taken is only 2 bits. Okay. Now, if I want to add the carry which was generated to the next bits, so for that, how many inputs I have to take for full adder? Is it 2 bits or 3 bits? How many bits I have to take for full adder, for making my full adder circuits to work?
3 bits.
3 bits. Okay, so I have considered 3 bits. So if I am considering the 3 bits, so what I am getting again, 1 plus 0 is 1, 1 plus 1 is 0. So sum is 0 and the carry is 1. So here we need to consider two outputs also. So 3 inputs and 2 outputs. So see here, so this is your 1 bit full adder. So in 1 bit full adder, first is what, three inputs that we have considered based on the half adder problem. In a half adder problem, when there is a carry generated, we are not adding as an input. So whereas in this, we are adding as an input. So here the problem statement initially will be, we identified problem statement and we identified that there are 3 inputs to be given for full adder and 2 outputs, So this is your full adder. This is your full adder with 3 inputs and 2 outputs. The inputs that I want to assign is A, B, C, and the output that I want to assign is one for sum, C for carry. Okay, C for carry. This is a full adder. Now I have to go for a truth table. So for going for a truth table, how many combinations will get, ma? Is it 4 combinations? Through
3, ma'am.
3 combinations we'll get. So let me explain that with a truth table. So we'll get A, B, C as input. Next, sum and carry as output. Okay, so we will be having 3 combinations. One is 0 0 0. Now tell me, if it is 0 0 0, what will be sum and what will be carry?
0, 0, ma'am.
0 and 0. Okay, next, 0 0 1. Now what is sum and what is carry? 1 0. Next is 0 1 0. Sum will be 1, carry will be 0. Next is 0 1 1. For this
0, ma'am.
0, carry also 0.
One, ma'am.
1. Okay. 1, 0, 0. Sum is 1, carry 0. Next. 1, 0, 1. Next. Sum is what? Sum is what? Roll number 39. Sum is what, ma, for this?
0, ma'am.
Okay. Carry?
1.
Okay. Next is 0. It is 1, 0, 0. Until 5 we completed. Until 5 we completed. Next combination is 1, 1, 0, 1, 1, 1. Okay. Now for this, what will be sum? What will be carry? Sum will be again 0, 1 and 1, 1. Okay, this is your truth table. So finally this is your truth table. Instead of ABC, it is mentioned here as the variables as XYZ. So XYZ and carry and sum. So do we got the same answer? Yes. 0, what we got? 0, 1, 1, 0, 0, 1, 1, 0, 1, double 0, 1. So 1, this is the answer you we have to get. Okay, so this is your answer. Okay, so next is what? Next is what? Next is truth table. So for truth table, tell me the expression. For truth table, how many variable k map I have to select? How many variable k map I have to select?
3 variable.
3 variable k map. Okay, so for 3 variable k map we'll be having 16 combinations to power 16 or 8 combinations, 8 combinations to power 3 a. So we'll be having 8. So a, b, b, c. So a complement a, b complement c complement, b complement c, b c, b C complement. Okay. Now let me write 0, 1, 2, 3, 4, 5, 6, 7. Where I have to place 1 for sum? In which combinations I have to place 1? Let me write the numberings so that it will be easy for you to understand. 0, 1, 2, 3, 4, 6, 7. Now tell me in which combination the output of sum is 1. For 1, isn't it? Is it 1? Yes. For 2, for 4, for 7. This is your output for sum. Okay. Is it possible? How many groups we have to do for this then? How many groups can I have? Can I combine entire as one group? Can I combine entire as one group? No. We will be getting 4 groups totally. We'll be getting 4 groups totally. So these are the 4 groups. Okay. Now tell me the expression for s equals to. Tell me the expression for s equals to. Okay. Now start with the first one. What will get? A complement. Is it finished, Ma? Can I erase this so that I will start from the starting? Is everyone written in your notes? Written in your notes, Ma? Until this truth table. This is your full adder. This is your truth table. We started with the 3 variable k map for sum. So for this now I need to start with, I'm erasing one. So I need to start with simplification process. I need to start with simplification process. So for that I'm writing the expression s equals to. So let me start. So s equals to, just tell me for this first one 1. Okay, so what we'll get? A complement, b complement, c plus, tell me for this, a complement, b, c complement plus, tell for this fast, ma, you answer for this.
A complement
A
B.
A B complement C
A B complement C complement plus A B C complement. For this A B C. Okay. So for this, if you see A B C is your answer. Now if you take A as common, A complement as common. If you take A complement as common, what we will get, ma'am? What we'll get? B complement C plus B C complement plus what is common here? A. Again A is common. So if you take A common, what will get? B complement C complement plus BC. Okay. Now which is equals to A complement. What can I substitute? What is this?
B XOR C.
1.
B XOR C. Okay. So here let me show the once again the XOR truth table so that you can understand even more clearly. So here this is your XOR gate. This is your XOR gate which is implemented as see the cursor position A XOR B, and this is your XNOR. You will get the output as A XOR B complement. Means here is what A complement. What's the output for this? For 0 0, the output for this is 1. Means what will be the expression for this? A 0 0 means 0 indicates complement. So A complement B complement plus here we have 1 1 means A complement. A is it AB? So A complement B complement plus AB, which is nothing but XNOR gate. Try to understand. For showing you, I have selected this PPT especially. XNOR gate. So XNOR gate, the output is 1 when it is 0 0, when it is 1 1. Means for 0 0, the expression will be A complement B complement, and for 1 here we have 1 1 means plus AB. So A complement B complement plus AB is nothing but XNOR gate. So is there any combination like that here? So this is your X XOR gate. This is why, because we have A B complement C plus B C complement plus what is this gate then? Is it
XNOR.
XNOR? So A B, in this way you have to represent. Okay, so this until here it is clear. Hope. Next, try to substitute X complement C as D. So what we will get? A complement D, substitute B complement C equals to D. So if you substitute, we will get A complement D plus A, what will get? A D
D
complement.
complement.
Okay. So A complement D plus A D complement, which is equals to what? Which
A
is it?
XOR D.
A XOR D. So try to substitute in D place what we have assigned. So finally what we'll get? A XOR B XOR C. So finally we got for the sum what? A XOR B XOR C. Okay. This is your output for sum. Then do it for carry. No? Everyone do it for carry. And listen all of you in the textbooks. Hope that everyone clear. Note down in your notes, please. Note down in your notes the steps that I have written. Next, we need to follow. It is until 10:20 only, no, ma'am? The time.
10:30, ma'am.
Okay, 10:30. Okay, let me complete the uh, carry also. So in a carry, just let me support Mima so that I will complete fast. So next is we have two outputs. So because of that, we need to select three variable k maps, one for sum and one for the carry. Next we will have A, B, C. So A complement A. Next is, let me write down C. Okay. Next is B complement C complement B B complement C B C B C complement. Okay. Where I have to place one? Just tell me where I have to place one in according to this table. Where is the table? According to this table. In
3, 5, 6, 7.
Okay. In place of 3, in place of 5, 6, 7. Okay, these are the ones that I have placed. Okay, so let me go for grouping. So if you want to go for grouping, you will group in this way, and in this way. Now tell me the expression finally. C equals to what? C equals to
AC plus AB plus BC.
AC plus
AB
AB plus
plus BC.
BC. Okay, so this is your carry, but in some textbooks, in some textbook, it will be grouping in this way. Let me explain. So why? Because in the what we are preferring the textbook, you have to know why we are getting that expression. Okay, so we either in two ways you can write. If this is a way or whatever that we have done in the textbook, also you can write. So where we got ones here, actually we have 1 1 1 1. So grouping this combination and grouping this individually, so that we are getting what x we will be getting XOR. Why? Because anyhow we have designed one XOR, we are using one XOR gate for sum. Is it any possibility for getting carry as XOR, so that we can utilize that? So this will, if you combine in this way, we'll be getting XOR. Let me check how we will get. Is written everyone this expression? Should I erase this?
Yes, ma'am.
Okay, so let me go for carry. So if it is the carry, so let me go for carry. C equals to, now according to this, tell me the expression now. For this first one, A complement BC plus, for the second one, A B complement C, next plus plus
AB.
AB.
AB. This is your expression. What can I do? Which variable I have to select as common in this two? Which
C, ma'am.
variable? C. Okay. C A complement B plus B complement C plus AB. Okay. Next is what? C. What can I write this as? A
A.
XOR B
XOR B.
plus AB. Okay. So there are two expressions you can write for carry. This one, this one. Okay. Two are valid. So now last is what? Logic diagram. So let me keep the expressions here so that it will be useful for me. Uh, Next is what? The logic diagram. For this logic diagram, first let me do it. Let me complete for sum. Sum expression is what, man? Sum expression is what? A sum equals to final, what expression we got? A XOR
Ma'am,
what, man?
ma'am, in the second line you have to see common, no, ma'am.
In the
Here we
second.
took C as common, no, ma'am.
Okay.
Ma'am,
In the second line you
third
have
line.
written A complement B plus B complement C, ma'am. I think it's A B complement A in the
Ah,
upper line.
yes, ma. Yes. Here, if I am considering C as common, good, ma, good. So A complement B and A B complement should be there. So here, instead of C, everyone need to write A. Yes, ma, good, noted. Okay. Next is what? Next for sum, what is the expression, ma? For sum, A sum expression చెప్పండమ్మా, simplified
A
expression.
XOR B XOR C.
Okay, A XOR B XOR C. And for sum, you can either select this one or either you can select this one. So let me start with sum. This is your XOR gate for, let me write for sum. Sum. Okay. So for sum, this is your XOR gate, and the input that I'm giving is A B A B AB, which is nothing but the output here you will get as A XOR B, and this and the other one is C. So directly you take one more input C and make XOR, so that you will get what finally S equals to A XOR B XOR C. Okay, this is your expression. Now let me do it for carry also. For carry also means A XOR B. Anyhow we got this, so you select this one. Are you getting? So we got anyhow for some AX or B. So for this, I am selecting from this output and this C. And what we have to apply for this two? What is A here? What we have to and okay. So and next A B is there, right? So A B, what is there? And again, then what is there between this two? What of or means you need to select this one. So finally what expression we'll get here? Carry equals to C into A XOR B plus AB. So this is your logical expression. So from this we have taken AB as one operand, C from this and C from this, and next is AB. Directly we have taken AB, and next is OR we have done. So that this is your logical circuit for full ladder. And this the homework is you do, instead of this substitution of carry, you do try to use this one and complete the logic diagram. Okay, so I will stop here. This is also correct, or even you can substitute in place of carry AC plus AB plus BC. So AC plus so until this diagram it is correct, and for this expression you will be getting 3 AND gates followed by 1 OR gate. So let me show the diagram in this also. So see here, what we have done is this one.